Hello ladies and gentlemen, fans of calculus. We're going to go over a review of our test. We had an AB Calculus third 9 weeks test covering some of the basics of integral calculus we've been working on recently. First problem, for the differential equation dy dx equals 6x squared minus 4x plus 5, find the general solution to the equation. So we're going to do that first. I'm going to just rewrite this. Dy dx is equal to 6x squared minus 4x plus 5. And we're going to do with this dx in the denominator is cross multiply. So we're going to have dy is equal to 6x squared minus 4x plus 5. And we're going to multiply all this by dx. And now to solve for y, we're going to take the integral of both sides of this equation, and in so doing, we're going to get y is equal to the integral of 6x squared dx minus the integral of 4x dx plus the integral of 5 dx. And integrating on the right side, we're going to have y is equal to 6x to the third power divided by 3 minus 4x to the second power divided by 2 plus 5x. And then we're going to add the constant of integration c. And simplifying, we're going to get y is equal to 2x cubed minus 2x squared plus 5x plus c. And so we have, friends, located what we call our general solution. So now we go to the second part of the problem. Next, find the particular solution where f of 0 equals 2. So what we're going to do is take our general solution and substitute in for our output 2, and then we're going to substitute in 0 for x. We're going to have 2 times 0 cubed plus 2 times 0 squared. All right, it's actually going to be minus, not that makes a difference. And finally, plus 5 times 0 plus c. So c is equal to 2. So therefore, our particular solution is going to be y is equal to 2x cubed plus 2x squared, or be minus 2x squared, rather. I got that in my head someplace. Minus 2x squared plus 5x plus 2. And this is what we call our particular solution. And I'm not necessarily looking to see these things labeled as specifically as I'm doing here, but I'm looking to see those two functions in place somehow. Next, 2, the acceleration of particles given by the function a of t equals negative 32 feet per second squared. If the velocity of the particle is 3 feet per second at t equals 0, was the position function for a particle given the particle starting position is 5 feet, as in x of 0 equals 5. So what it is we have, we're looking here to take advantage of something that there's a hierarchical relationship between position, velocity, and acceleration. And if you have position function, you can take the first derivative of that to get the velocity, and the second derivative will get you to acceleration. But in integration, we go the opposite direction. We go from, in integrating, we go from acceleration to velocity, and subsequently from velocity to position by integrating, and that's what we're being asked to do here. So what we have here is we're starting out with a of t, but we want to get from a of t to v of t, and so v of t is equal to the integral of a of t dt, which in our instance here is going to be negative 32, and the units feet per second squared, we'll say, yeah, feet per second squared. So it'll be the integral of, that's what integral negative 32 dt we'll call it. And so now we can integrate this. V of t is equal to, I'll put negative 32 integral of dt, which is going to be equal to negative 32t plus our constant integration c. So that's like our general solution. And so next, we know the velocity of the particle is 3 feet per second at t equals 0. So what we're going to do is put in 3. I'm going to say v of, I'm going to write like this. Okay, since v of 0 equals 3, we'll say 3 is equal to negative 32 times 0 plus c. So c is equal to 3, and so now we have our particular solution. So v of t is equal to negative 32 t plus 3. So next, our position function x of t is equal to the integral of v of t dt. And so in this case we have x of t is equal to the integral of negative 32 t plus 3, and that's going to be dt. And integrating this, we have x of t is equal to negative 32, we have t squared over 2, and then we have plus 3t plus c. And so now I'm just going to bring this up here and kind of rewrite this. We're going to have x of t is equal to negative 16 t squared plus 3t plus c. And so now we're going to take in, we have since, I'll write down since x of 0 is equal to 5, then we'll have 5 is equal to negative 16 0 squared plus 3 times 0 plus c. So c is equal to 5. So our final position function is going to be x of t is equal to negative 16 t squared plus 3t plus 5. So that's our final conclusion here. So let's go on to our next problem. Problem 3 is a 13-foot ladder is propped up against a vertical wall. If the bottom of the ladder is moving toward the wall at a rate of 4 feet per second, at what rate is the top of the ladder moving up when the bottom of the ladder is 5 feet from the wall? So what I'd like to do for these is make a little sketch So we have this sketch here, and so we have this ladder. So we have this ladder here that is 13 feet long. So this is 13 feet right here. And we have, if the bottom ladder is moving toward the wall at a rate of 4 feet per second, so if we let this be like an XY coordinate plane, so we have a ladder that's moving toward the wall at a rate of, we'll call this dx dt, and that's going to be equal to, we'll say, negative 4 feet per second. And then it says when the ladder is 5 feet from the wall. Let me get a little skinnier pen here. So we have the ladder 5 feet from the wall. So if this is 5 feet right here at the base, and then ask the question, at what rate is the top of the ladder moving up? Well, it gives you, could say what rate, but it's giving you a hint when you say moving up. So we're going to call this dy dt is equal to question mark. And so now we're going to kind of do a scavenger hunt on what we have, what we're looking for. So we're going to find dy dt. When we'll have x is equal to 5, and we are given that dx dt is equal to negative 4 feet per second. And this is why the drawing can be helpful, because we can clearly, I hope, picture that our dx dt is going to have to be negative. And our equation we're going to have is none other than a version of Pythagorean theorem. But in this case, we're going to use x squared plus y squared is equal to our hypotenuse squared, which is 13 squared. So next we're going to take the derivative of this equation. So we're going to have our derivative of x squared is going to be 2x dx dt plus 2y dy dt, and that's going to be equal to our derivative of the right side, which is 0. And now we can go ahead, we're trying to solve for dy dt, and we can do this algebraically, but I'm going to go ahead and just substitute numbers in here first, as we have all we need. So we have 2, and so x is going to be 5, and dx dt is going to be times negative 4, as in negative 4 feet per second, plus 2, and y is going to be, if we use the Pythagorean theorem, we're going to have a squared minus, we have b squared equals c squared minus a squared. So you're going to have b squared, we'll say y squared is going to be equal to 13 squared minus 5 squared. So y squared is equal to 144. So y is equal to square root of 144, which is plus or minus 12. But in this case, we have plus 12. We have 2 times 12 times dy dt. And that's going to be equal to 0. And 2 times 5 times negative 4, that's going to be negative 40 is going to be equal to, negative 40 plus 24 dy dt is equal to 0. and then adding 40, we'll have 24 dy dt is equal to 40, and dividing by 24, we're going to get dy dt is equal to 5 over 3 feet per second. So that's going to be our answer to problem 3. Got classic related rates problem. Next, a rectangle's width is increasing by 2 centimeters per minute and its length is increasing by 5 centimeters per minute. What is the rate of area increasing when the width is 4 centimeters and its length is 7 centimeters? So we have this basic situation. We have our rectangle right here like this. We have our width. Our width is equal to 4 centimeters. Our length is equal to 7 centimeters. And our length is increasing. dl dt is going to be 5 centimeters per minute. dw dt is equal to 2 centimeters per minute. So find, what are we trying to find? How fast, what is the area, what is the rate of increase for the area? So we have dA dt is what we're trying to find. When, well, the length is equal to 7 centimeters, width is equal to 4 centimeters. We are given that L is equal to 7 centimeters. Nope, we already have that. When you're given that dl dt is equal to 5 centimeters per minute and dw dt is equal to 2 centimeters per minute, and then our equation is going to be that of a rectangle. Area is equal to length times width. And so just coming to the right, we're going to take the derivative of both sides. We're going to have dA dt is equal to, we're going to use our product rule. We're going to have, if we let one be u and one be v, we're going to have L times dw dt plus w times dl dt, and so dA dt is equal to our length, which is 7, times our dw dt, which is 2, plus our width, which is 4, times dl dt, which is 5. So we're going to add these together and get 14 plus 20, or 34. So dA dt is equal to 34, and it's going to be cubic centimeters per minute. So that's it. So a couple of related rates problems, pretty classic type problems. Next, 5. Starting at noon, snowfall rate readings in inches per hour are taken at 1 hour intervals until 6 p.m. Use the trapezoidal method with 6 subintervals to estimate the integral from 0 to 6, ft dt, give correct units and interpret the meaning of your answer. So the estimate of the integral of from 0 to 6 of f of t dt, and it says give 6 subintervals, and so that's a signal just to draw 6 blanks. 2, 3, 4, 5, 6. So you have 6 blanks, and it says we are in inches per hour, so the units here are going to be inches because we've eliminated the rate when we've integrated here. Now using the trapezoidal rule, and the area, I'm going to just write this up here. The area of a trapezoid is equal to 1/2 of the height times base 1 plus base 20 base 1 plus base 2. So we're going to use all that. So we have here the first one. We have our, I'm going to put for trapezoid rule, I just put 2 underneath all of these. And all these trapezoids are going to have a height of 1. So we're going to have 1. I find that organizing it this way just eliminates a lot of opportunities for errors. So height, and then we're going to have base 1 plus base 2. Well, in this case, we're going to have the first one. We're going to be between it's going to be 0.5 plus 1.2. For the next one, we're going to have 1.2 plus 2. The next one, we're going to have 2 plus 1.5. Next, we're going to have base 1 is 1.5 plus 0.8. Then we're going to have the next one 0.8 plus 0.7. And our last trapezoid is going to have a base 1 of 0.7 plus the base 2 of 0.4. And we could go ahead and simplify and get this down to one number, but we don't have to do that. That's a simplification that we don't need to do right now. And it says we have the correct units, inches, give the meaning of your answer. So so this will be the inches of snow that fell between noon and 6 p.m. So that'll be our interpretation of that answer. Next, 6. Using graph below, use a right Riemann sum to estimate the area under the curve over the closed interval from 0 to 7. Use 7 subintervals. Also tell if you think the estimate is overestimation or an underestimation. So I'm going to go ahead and just move this over here to leave more room on the left side. And so we're going to have okay, so we'll say estimate of, we'll say 0 to 7, and we're going to call it f of t or f of x. We'll call it f of x dx. We'll call that. And that's going to be equal to, I'm going to get 7 subintervals, so 1, 2, 3, 4, 5, 6, 7. And so it's kind of hard to read some of these here, but basically all these input values are 1 unit apart, so our rectangles, each one is going to be 1 in width. So I'm going to put 1 here for each of these. And one thing that can be done for organization's sake is this can be changed into a table. So if we go ahead and make a table here, if we have x, f of x, we can just see what's happening. We have, first of all, 0, 0. The next one we have is 120. Next one we have here is 2, 36. Then we have 3, 48. Then we have 4, 56. We have 5, 60. And then we have 6, 60. And finally we have 7, 56. So we're going to use the right values here. 1 times 20. The next one here is going to have 1 times 36. Then we're going to have 1 times 48. 1 times 56. 1 times 60. 1 times 60. And finally 1 times 56. So, and it doesn't give what units are. This would be a right answer. Now, the last thing, tell if you think your estimate is an overestimation or an underestimation. And basically what the rectangles are going to be like this. The Riemann sums are going to be, you're taking, the first rectangle is going to be this one right here. A width of 1, but a height of 20, so we're going to be like this. The next one is going to be a rectangle that goes up like this. It comes down. So it's this rectangle. And then the next one's going to be like this. Okay, so we have this rectangle. So you see what's happening here? As long as we're increasing, this one here is going to overlap the top of the curve like this. This one here. So a lot of overlapping. Then it's going to be neutral here since we're going from 60 to 60. And really the only one that's going to be an underestimation is this last rectangle on the right. So since in this is kind of axiomatic, since the function, since f of x is increasing over most of the domain, a right Riemann sum is an overestimation. Is an overestimation. And really, when you say it like that, it's an axiomatic thing that just by definition of a function is increasing, a right Riemann sum is an overestimation. If a function is increasing, a left Riemann sum is an underestimation. So it's just a rule, really. Okay, next. 7. What is the integral of x times quantity x squared plus 3 to the 5th power dx? So we could go ahead and expand this x cubed plus 3 to the 5th power, and then we could distribute the x to all that, and we'd have a situation where we could actually perform this integration, but there is a shorter way to do this, which is called a U substitution. What we can do is we can take this portion inside that's raised to the power of 5 and let that equal to U. So we said let U equal to what's inside, or x squared plus 3. And when we do that, we're going to have du dx, derivative of u with respect to x, is going to be equal to 2x. And then cross multiplying the dx, we have du is equal to 2x dx. And so dx, therefore, is equal to du over 2x. And what we're going to be able to do with these substitutions is cancel this single x right here. And so we're going to show what that is. So that's going to be equal to the integral of x, and now substituting in u for this x squared plus 3, that's going to be u to the 5th power. And now substituting in for dx, du over 2x, we have a cancellation here, so that's going to be equal to 1/2 the integral of u to the 5th power du. And now we can take this u, the integral of u to the 5th power is u to the 6th power, and we're going to divide by 6, which is the same as multiplying by 1/6. And we're going to not forget our constant integration c, so what we're going to get is we're going to get 1/12 u to the 6th power plus c. And then we can substitute in for our original u and get 1/12. We're going to have in the place of u squared plus 3. And that's going to be to the power of 6 plus our constant integration c. So that's what our answer is there. Next, we're going to go to our last problem here, was the integral of 4x squared times the square root of quantity 2x cubed minus 2 dx. So in this case, we're going to take what's in the radical here. We're going to let u equal to 2x cubed minus 2. And so du with respect to x is going to be equal to 6x squared. And cross multiplying the dx, we're going to have du is equal to 6x squared dx. And solving for dx now, dx is going to be equal to du over 6x squared. And now we're going to substitute in here with the integral of 4x squared, and we're going to have this square root of, well, that's going to be u, so that's going to be u to the 1/2 power 4x squared, u to the 1/2 power, and we're going to substitute for dx, which is going to be du over 6x squared. How convenient. We've canceled out the x squared over x squared. So now what we have left is 2/3, and that's simplification of 4 over 6. We're going to have u to the 1/2 power du. And now, using the power rule, that u to the 1/2 is going to become u to the 3/2, and dividing by 3/2 is the same as multiplying by 2/3, and plus c, so that's going to be equal to 4/9 u to the 3/2 power plus c, and just kind of working ahead to the right, we're going to have 4/9, substituting back in. Our u to 3/2 is going to be, our u is going to be 2x cubed minus 2 to the 3/2 power plus c. And we can keep it there as a correct answer. Some of you may want to go ahead and put this back into a radical form, which is going to be to the 3/2 power is going to be like this. We have 2x cubed minus 2 in parentheses to the 3rd power and plus c on the outside. Either of these will be correct expressions. So that's all there is to it. I hope this is helpful to you. Good luck and thanks for viewing.